Hello, my name is Charlie Joyner. Hello, this is my A2 presentation on biomechanics. In this presentation, I will cover distance and displacement, and we'll be going through some examples, speed and velocity with some examples, distance time graphs, and velocity time graphs. Each one of these are either a scalar quantity or a vector quantity, which I will be covering. First one I'll be going through is distance. Distance is used in all kinds of sports to help athletes track their progress along and make sure they're on the right track and training at the right level. An example of this could be a runner preparing for a marathon. They may train every day but at different speeds to help them build up the ability to run a marathon, which is in the best and fastest way possible. This means that the athlete will monitor distance to help them keep on track. Distance is also used to track their progress as an athlete starts training and struggles to run a 400-meter without becoming out of breath, but within a couple of weeks they realize they can run further and further without fatiguing. This shows that the athlete is improving and their training is working. The equation of distance equals speed times time. Using the equation in an example would be like this. A sprinter ran at a speed of 3 meters per second for 60 seconds. What is the distance the sprinter ran? So we do 3 times 60, which is 180 meters. Another example could be a cyclist traveling 300 kilometers an hour for 4 hours. What is the total distance the cyclist cycled? So you would times the 30 kilometers an hour by 4 to get 120. So the cyclist cycled 120 kilometers. Next topic is displacement. Displacement is the length of a straight line joining the start and finish points, the quickest route from A to B with direction. This means displacement is a vector quantity. The equation for displacement is displacement equals velocity times time. An example of this in sport is a cyclist cycling. If the cyclist has a velocity of 6 meters per second and travel for 20 minutes, what is the displacement? So you do 6 times 20 to get 120, because it's measured in meters, it'd be 120 meters. Also, as displacement is a vector, it needs a direction, so you'd say 120 meters north. Displacement is crucial for some athletes to understand as it can help improve performance, for example, a long jumper, as displacement is not just about horizontal distance, but is also about vertical and lateral movement. So by understanding displacement, the long jumper can find out the best, most efficient way of jumping that will get them the farthest. Another component of sport is speed. Speed is defined as the ability to move parts of your body quickly, or the rate at which someone can perform a movement or cover a distance. Speed does not have a direction, meaning it is a scalar quantity. The equation for speed is speed equals distance divided by time. An example of speed used in an equation is a sprinter runs 100 meters in 20 seconds. What was the speed of the sprinter? Using an equation, you then divide distance by time. So 100 divided by 20, which is 5. And speed is measured in meters per second. So it's 5 meters per second. You can use this equation to also calculate distance and time. Using the speed equation triangle, which will help you calculate speed, distance, and time. For example, a cyclist was cycling at a speed of 4 meters a second and cycled for 25,000 meters. How long did the cyclist cycle for? So you do 25,000 divided by 4, which is 6,250 seconds. And if we wanted to put that in hours, we divide 6,250 by 60, which is 104.2 minutes, and then divide by 60 again, which is 1.7 hours, which is roughly an hour and 44 minutes. Speed is a very important measurement in sport, and athletes use to track their progress. For example, sprinters calculate their speed to check if their training has worked and they're improving, or if they're not, then change the training to be easier or harder so they can train at the right level effectively to get their goal. The next thing we're going to cover is distance time graphs. Distance time graphs are used to show us the journey, distance traveled, of an athlete and can show us the speeds they travel at. So if you look at the graph, you can see the different points labelled is where athletes change their speed. If you look from A to B, you can see that the athletes accelerated as the amount of distance went from nothing, 0, to 3. However, from B to C, you can see that the athlete is stationary as it doesn't change from hour 5 to hour 8. So for 3 hours they didn't move. Then from C to D, the athlete has a massive acceleration. Next, the athlete had another break from D to E as this distance isn't moving again, which means they are stationary. Finally, E to F is acceleration, but in the opposite direction. The whole time the athlete was going in the same direction, in the same north, but from E to F, athlete turns around and accelerates in the opposite direction. Distance time graphs are used to calculate the speeds of athletes. In this example, the athlete is running a 24-kilometer, which is just above a marathon, from A to B by looking at B at the y-axis, which tells us the distance the athlete covered from A, which is 3 kilometers. Then we go down and look at the x-axis, which tells us the amount of time he took to run 3K, which is 5 hours. So then we put that into the equation and do distance and divide it by time. So 3 divided by 5, which is 0.6 kilometers an hour. So from A to B, the athlete is running at 0 kilometers an hour. Then from B to C, the athlete is traveled at 0 miles per hour as they've traveled 0 kilometers an hour. Then from C to D, the athlete traveled 9 kilometers in 4 hours as you count from when he started running again. So from here where C is. So now we divide 9 by 4, which is 2.25 kilometers an hour. So now we can see that the athlete is traveling a lot faster than when they started the race. From D to E is the same, they're not moving, so the speed is 0 kilometers an hour. Finally, from E to F, the runner turns around and starts going back where they originally came from. The athletes go the whole 12 kilometers back in 6 hours. So now we do 12 divided by 6, which is 2 kilometers an hour. So using the distance time graph, we can gather when the runner has been running and for how fast. We then have velocity, which is the displacement of an object over a time with direction, meaning velocity is a vector. The equation for velocity is average velocity equals displacement divided by change in time. Velocity is measured in meters per second minus what? We can use the equation in an example. If a baseball traveled 200 meters north for 5 seconds, what would the velocity of the baseball be? So you do 200 divided by 5, which is 40 meters per second north. Velocity time graphs are used to calculate the rate of acceleration and deceleration, but also shows us if the athletes are traveling at a constant speed. We can see the different lines what the athlete is doing. So we can see the first line is pink and is at a gradient, which means it's acceleration as the athlete is increasing velocity as time goes on. The next bit is flat and is at a constant speed as the athlete is traveling at the same velocity as time goes on. The green is deceleration as the velocity is decreasing over time. The whole bit underneath, this whole space here, is the distance the athlete would have traveled. This is an example of a velocity time graph of a cyclist. First, to be able to get the displacement before we multiply velocity by time. We will have to get the minutes into seconds So every time we get the time, we have to times it by 60, as there are 60 seconds in a minute. Then do the equation. So when you're trying to find displacement for B, it's easy as the cycle is traveling at a constant speed, so from 10 to 20 minutes. So we do 10 times 60, which is 600. So the velocity is 4. So 4 times 600, which is 2,400 meters. Now we can find the displacement of A, but in order to do that, we need to find out the average velocity, as the cyclist is not traveling at the same velocity throughout this last bit. So you'd find out the average velocity by subtracting initial velocity by final velocity squared, and then do the normal equation from there. And this is my bibliography.